It is a pleasure to introduce the last talk of this afternoon. Professor Dr. Klaus Mainzer is very well known here at TUM. He was my predecessor at the chair of philosophy and theory of science. So for me, it's a very heavy heritage to be the successor of such a professor. And he is also Emeritus of Excellence by us at TUM. And he is senior professor at the University of Tübingen, which is also a university of excellence. And he is really trying to bring critical thinking in the natural sciences and technologies. So I'm very proud to announce your talk, Professor Mainzer, from the quantum world to quantum AI. So the floor is yours.
Yeah, thank you very much. And now in the end, philosophy in the evening. And that is in the sense of Hegel. And you know, concerning a famous quotation of Hegel, in the evening, when the shadows of sciences become longer and longer, then the owl of Minerva, and that means philosophy, starts its flight in the twilight. But I am not a Hegelian. I am a Cartesian. And following René Descartes, the great French mathematician and philosopher, philosophy comes in the beginning, in the principles, in the philosophical principles of science. But these principles must be mathematized and then in the end experimentally tested. And Principia Mathematica Philosophiae Naturalis, the title of the famous textbook of Isaac Newton. Now, in that sense, I will start with the principles of the quantum world, then the principles of quantum computing, building up of them. There will be some intersections with Marisa. And then in the end, building up of this basis, classical AI, and then quantum artificial intelligence. Now let's start with the principles of the quantum world. And here in the beginning, there is a remarkable observation. You see on the left the classical belief that the movement of a solid body has this kind of sharp trajectory. But if we do measurements with quantum systems, for example with photons and so on, then we observe scattering. And therefore, following Richard Feynman, great Nobel Prize winner, US physicist, we have to sum up all possible passes of a particle between two positions. And that means in the end, quantum states are probabilistic distribution. And that is founded in a first fundamental principle, namely Heisenberg's uncertainty principle. And that does mean that it is not possible to determine, for example, location and momentum of a particle with arbitrary accuracy simultaneously. But it depends from one another. If you try to measure location better and better, then momentum starts to scattering and vice versa, depending on the fundamental natural constant H Planck's quantum, because that is the smallest unit of energy in the universe. And here we see we are no longer in a classical world in the sense of Leibniz with infinitesimal small unities, but with finite discrete unities. And the second principle, superposition. And we also in the classical world, we are familiar with the idea that properties are independent from one another and exclusive. For example, in a classical computer, here computer is in the state 0 or it is in the state 1, either or. And in the life world, we know an organism is dead or alive, but in the quantum world, it can be superposed. And that was illustrated in a famous thought experiment by Erwin Schrödinger in 1935. That was an annus mirabilis for the foundation debate. I will come back to other examples later on. And he illustrated in this thought experiment, there is a box is closed, and in the box is a cat, and radium preparation. The radium preparation is a quantum system which can decay by equal probability, and it is assumed that decaying initiate a hammer mechanism here, and the hammer mechanism will destroy a bottle of hydrocyanuric acid, and that would of course kill the cat. But in the Schrödinger interpretation, the whole box, closed box, is considered as a quantum system. And that means as long as the box closed, the cat is dead and alive, depending on the decaying radium preparation with equal probability. But in the case of measuring the quantum system, and that would means here that we open the box, then in the interpretation of Schrödinger, the wave function of superposed both states, dead and alive, will rapidly collapse. And what we observe is the cat is either dead or alive. And that, by the way, was discussed in the booklet here on the right, which we published in the 80s. And I mentioned this book because there were famous contributors, for example, Peter Mittelstädt. And Peter Mittelstädt was a former co-worker of Werner Heisenberg, the last Habilitant, German speaking, and he was a close colleague of Marisa, and he was host and lecturer of our philosopher in residence, Roberto Giantini. And Anton Zeilinger, the young Anton Zeilinger, was also one of the authors in our book. But that was absolutely not acceptable for Einstein, because Einstein was a classical physicist, and here in the picture we see him in an engaged discussion, controversy discussion with Niels Bohr. Niels Bohr was the head of the young quantum physicist in that time, Heisenberg, Wolfgang Pauli, and Schrödinger even sometimes from Austria was joining them. And for Einstein, the world must be completely determined. But what Einstein did, he discovered a third fundamental principle here of the quantum world for the first time, and that is entanglement. And what does it mean? Einstein argued for the first time, if we believe in the quantum formalism, then it must be possible that an object, measuring an object at one location, would immediately react and influence the properties of an object on a far distant, different object. And that seems to be, for him, spooky. Why? It seems to contradict to his famous principle of the velocity of light. Light as the fastest velocity of signals in the universe. And but that was Einstein. Einstein suggested now an experiment, and that is the famous Einstein-Podolsky-Rosen, the EPR experiment. And that means, suggestion of Einstein, that we have a common center with prepared entangled pairs, for example, of photons, and then they are emitted in opposite direction and then are measured. And then we will see what will be the results. Now, you remember I'm a Cartesian. That is a philosophical principle of a certain interpretation of reality of Einstein, namely so-called local reality. Local reality means there are locations and all events on these locations are independent from one another. Now, mathematization, that was John Bell. John Bell, Irish physicist from CERN, and he suggested the Einstein experiment in the following way. Following this illustration here in the center, there is a source with prepared pairs of photons. By the way, nowadays, what does that mean? Nowadays, we use, for example, a nonlinear crystal and send a laser beam to it, and then the crystal will emit these photons in different direction, in the direction here of filters characterized with certain patterns, with certain settings here. The settings depend on certain angles here, A and B, and A stroke and B stroke. And if a photon passes a filter, then it gets the value 1, and if it is reflected, the value -1. And then school math, by simple calculating here, multiplying, adding with 1 and -1, we will get this term you see here on the right, in this inequality, because this term is between exactly -2 and 2. And that is a mathematical, simple consequence from the Einsteinian philosophical principle of local reality. Now it is illustrated here on this slide in this interval, -2 and 2, depending here on the different angles and the angles between A and B and A stroke and B stroke are supposed to be equal. And then the experiments were done in the beginning of the 80s, and Alain Aspect in Paris and other, especially French physicists. And then what did they observe? This curve here. That means quantum mechanical measurements, significant deviations from the predictions of the classical Einsteinian principle. And in that sense, this assumption of Einstein was rejected. And I had the chance in the 80s, that was the time of my first professorship in Constance. And I had a simultaneous appointment at the ETH Zurich. And there we invited nearly all these people who are here mentioned, for example, John Bell. And I remember very well Abner Shimony. You mentioned him. Abner Shimony, I cooperated with him. Later on, he was first a professor for physics at the MIT and then a professor for philosophy at the University of Boston. And he always said, what are we doing? We are doing metaphysics, because we are discussing the old metaphysical question, what is reality? But the difference is we draw consequences and we do experiments. So what we are doing here, experimental metaphysics. Principia mathematica philosophiae naturalis. Now, the principles of quantum computing. And here we start with classical logic, the classical world, and Marisa already introduced the main issues here. Here is a survey of the logical connectives and not and or, exclusive or, and the swap connective exchanging here in the right, exchanging the two inputs as two outputs, or the copy connective, for example. And you know, in logic, these connectives are defined precisely by the truth tables. Distribution of 1 and 0, that means the truth values. And now technology comes in. You can interpret these truth values as technical states, namely, for example, a lamp off or a lamp on. And I remember when I was a schoolboy, I was absolutely fascinated by this first idea, very simple, today I would say, of AI, namely that logical thinking can be realized technically by this kind of circuits with lamps and with lights. And later on, in the end of my talk, I will come back to my early fascination at school with lamps and lights. Now, the next step, of course, is what you already mentioned, the interpretation of that in quantum technology. Of course, a quantum system can be characterized here in my example by polarized states, quantum states, horizontal or vertical polarized. You know that now with the sunglasses, the polarization. And 0 and 1 are represented by these states, but now they can be superposed, Schrödinger. And that means you can consider all these continuous degrees between 0 and 1, and that is mathematical. You mentioned it already. That is mathematical expressed here by a vector. The vector psi here in the Dirac notation, the vector notation. And that means very simple. That is also school math. The vector is spanned over the coordinate system with the two vector units, 0 and 1. That's all. And these coefficients here, but then, and that is also school math, simple consequence of the theorem of Pythagoras, namely the absolute value of these coefficients, A0 and A1 added is 1. That is the theorem of Pythagoras. And that allows to interpret these coefficients as probability, namely the probability to be more 0 or to be less 1, and vice versa. But we cannot only superpose 2 bits, but we can superpose unbelievable many bits in a superposition, and that allows that we are not enforced to calculate, such as in a classical von Neumann computer, to compute step by step each bit, but we can consider an unbelievable large superposition of bits, and then we can apply a computational device to the whole superposition. And that allows an enormous acceleration of computation nowadays, and that is one of the great advantages, of course, of the quantum computer. Then in the end you can handle problems now at the quantum computer, at least in theory nowadays, which would not be possible to handle them with the classical computers. And that is illustrated here in the second picture, the superposition of these bits, which are here elaborated by a quantum computer. And what is a quantum computer? It is built up by quantum gates, such as a classical computer, which is built up by classical gates. But what are quantum gates? We heard a little bit about that already. In order to understand that, we remember that the quantum bits can be represented by state vectors. And the state vectors can nicely be interpreted in elementary geometry by the so-called Bloch sphere. That means we consider again a simple coordinate system with the x, y, and z axis. And in the origin of this coordinate system, there is the origin of a sphere with a unit radius. And the vectors are pointers in the sphere which can rotate around the origin, and they point to the points on the sphere, on the surface of the sphere. And these points represent the quantum states. For example, here in the picture at the 2 poles of the sphere, there are our extreme values, 0 and 1. And the pointer is now rotating, and here with equal distance to 0 and 1, we have exactly the situation of Schrödinger's cat, namely with equal probability. And these state vectors are now interpreted in the quantum formalism as operators defined on the state space of a quantum system. That means the so-called Hilbert space. And these operators are reversible by definition. And that is quite different to the classical world, because we know, I mentioned that in the beginning, for example, the OR connective, if you have the output 1, then you have several possible inputs to lead. It's not unique. These different inputs which can lead to the output 1. And these operators can now be technically interpreted as gates. And we heard about that already, some aspects here, a survey on the X, Y, and Z operators concerning the 3 axes here. And the X operator concerns the NOT gate, the classical NOT gate flip-flop. You can imagine on the Bloch sphere, the pointer is jumping between the 2 poles, and mathematically that is represented here by simple school math. That means simple matrix here, the distribution of 0 and 1s applied to the vector representation here of the 0 quantum state. And simple calculation leads us from 0 to 1 and vice versa. And here below there is a rotation operator which describes a rotating pointer. And here are the already discussed Hadamard operator. It's also school math. It is a simple matrix, and calculating here with a vector again leads to a superposition, which is now well known, the superposition of Schrödinger's cat with equal probability. And here the controlled net operator, which leads us to an entangled state here in the second example here. And that means in the end we get a state, an entangled state, which cannot be separated in different states. I explained it in the Einstein discussion, and mathematically speaking, it cannot be written as a tensor product, and so on and so on. And here in the book and other books, the details are for the further operators are explained. Now, in the end, we have an idea of what a quantum computer is. A quantum computer is built up, such as a classical computer, with different layers. And here in the vertical order on the left, there is the input layer, like in a classical computer, representing the bits, and the bits are representing by arrows up and down, and representing 0 and 1. But then we want to use the advantages of quantum parallelism, and that means in the second layer we apply the Hadamard operators to transform the bits in superpositions, and then step by step all other necessary quantum gates are applied. So an algorithm, a quantum algorithm, is nothing else than a connection of different devices, quantum gates, such as in a classical algorithm, we have a connection of different classical gates. But in the end, in the quantum case, we get again a superposition. And that means a superposition of all possible results. And that is, of course, very different to the classical world, because in order to read out the correct result, we have to measure this superposition. And we know that from the quantum case of Schrödinger, that then the superposition would collapse into all these possible results with equal probability. And that is, of course, a problem. In a stupid way, we could start to check each result step by step for n elements. That would mean n steps, which cannot be handled for huge numbers. And so we have to improve this outreading algorithm. And that was first done by the so-called Grover algorithm. The Grover algorithm can reduce the abilities from ordering n to the root of n, but that's also not handleable. Nowadays we have algorithm which can do that. For example, the fast Fourier transformation in a quantum version in a practical way. That is a background of nowadays working quantum computers. Now, my last part on this background, quantum AI. First, classical artificial intelligence. And perhaps you know, classical artificial intelligence nowadays use simplified models of the human brain. These are the so-called neural networks. And here are the architectures illustrated in that slide. It consists of nodes. Nodes represent the neurons, and these arrows represent the synaptic connections. And the arrows in the model are weighted by numbers. The numbers indicate the neurochemical intensity of the neurochemical signals in the brain. And then it is said that the node is excited, a cell is excited, or is firing, or is generated a bit if the sum of the neighbored weighted inputs, the neighbored cells, is larger than a certain threshold value. And by that you get a sequence of signals, which a data stream, which is led through the architecture here of a neural network. And the network is layered, by the way, such as the neocortex of the human brain. And the data streams are triggered by so-called learning algorithms. And there are several kinds of learning algorithms. I will only mention one or two. The supervised learning algorithm means that at first the neural network is trained by a prototype, therefore supervised, for example, a face. A face is a distribution of colored pixels. And then we can change the weights, which I mentioned, in order to train, to represent the face in the neural network. And then the learning in case of supervised learning, the system is able to recognize this trained prototype of a face among a huge number of other faces, perceived faces, which is used by police hunting, for example, since many years for hunting criminal persons by their faces. And then in the end, deep learning. Deep learning has nothing to do with philosophical thinking, very deep thinking or things like that. It only relates to the number of layers. And I mentioned already the neocortex of the human brain have 5 layers, and here in this example there are 4 layers. But here it is working quite similar to the human brain. That means on the first layer only colored pixels are distinguished. Next layer the pixels are connected as edges and corners. Then partial faces are recognized, and in the end the whole faces. And that is all. That is machine learning. What is modern machine learning? It is nothing else than pattern recognition in big data by learning algorithm. And here's some nice examples in medicine. For example, pattern recognition in breast cancer, supervised learning. The system is at first trained with the criteria of cancer, and then it is able to distinguish here in red the distribution of the cancer cells from, in green here, the distribution of the healthy lymph nodes. But what are these algorithms? These algorithms nowadays applied in artificial intelligence were well known in physics for long ago. here in the picture applications for pattern formation, not recognition, pattern formation for structures in nature. For example, here spin glasses, or here a complex system of a ferromagnet. A ferromagnet consists of elementary dipoles. The arrows showing up and down, and then the whole system is cooled down. That is, physically speaking, phase transition. And then it is led to an equilibrium state, namely an equilibrium state as a so-called Curie point in this example, when all these dipoles are showing in the same direction. And that means they are in the same microstates and they enforce themselves, and that means a magnetization of the whole system. And this kind of algorithm was applied by Hopfield. Hopfield was a physicist. And here you see the influence of physics for innovation, which was mentioned by Wille in his talk. And he applied this phase transition here as learning algorithm for the Hopfield system. That means a network with only one layer with alternative states here, black and white. And then again the system is trained, and there is a target ordering connected with the equilibrium state here, the so-called attractor, and that is the ordering here of the letter A. And then we interpret this kind of phase transition as pattern recognition of the system. And now we can transform it into the quantum world, and that is illustrated here. No longer bits with 0 and 1, black and white, but they are interpreted here by spheres, our Bloch spheres, with the rotation pointers here in order to degree the different probabilities of state, and that is illustrated here in a simplified way for the Hopfield system. Not only 0 and 1 here in the Bloch sphere by the different pointing to the poles of the Bloch spheres, illustrated here 0 and 1, black and white. And here also this vector position with equal distance to the poles. That means the Schrödinger state, which is here indicated by the color gray in these squares in the Hopfield layer. And by that, the same algorithm, which I described in the classical way here on the right, is moving in the direction of the trained attractor, the equilibrium situation. Maybe this is here the simplified shape of the letter C. Now that must of course be translated into the quantum formalism, but actually in this way we can describe the situation for one layer. But modern neural network, real world neural network, do not have only one layer. They do not only have 5 layer like the neocortex of the human brain. The neural networks here in the center of BMW for car industry and automatic car driving, they have thousands of layers. They have millions of neurons. They have billions of weights. And that is illustrated here in the picture, mathematical described by a network function, depending here on a certain input, and theta means the distribution of all these many weights, and these weights must be trained to theta star here on the right. The network function must in the end approximate the so-called target function f, which describes the target of the system, for example, recognizing a certain pattern. And nowadays the computer scientists are claiming the so-called black box problem, because they argue nobody knows exactly what is going on here in the detail, but actually from a mathematical and physical point of view, I must say no problem. Because then since over 100 years in mathematical physics, we are considering such kind of complex systems. Boltzmann, thermodynamics, statistical mechanics, what is liquid, what is a gas. It is a complex system of billions of interacting molecules and now neurons. So we have the mathematics, and in the mathematics, this mathematics we can use to describe a so-called Boltzmann machine. That means here the neural network with several layers, but in a stochastic way. It is now a stochastic machinery. And of course, remember my examples. That is a question equilibrium phase transition of energy distribution. And so we have here on the slide the energy folly concerning the energy distribution depending on the interaction of all these neurons. And then the learning algorithm is actually the stochastic process in that models leading the system to equilibrium states. And by that we can nicely, still with the classical Boltzmann machine, nicely solve so-called optimization problems. For example, optimization problem of traffic flow. Is the traffic flow, should it be homogeneous, or is it chaotic, or only locally homogeneous? No, it should in general be homogeneous. How can we do that? The machine must go to a global equilibrium point, and that is illustrated here with the energy landscape over the different constellations of the elements here, the neurons, and then we get this kinds of curve with different local minima, for example, but we do not like a local minima, only for a local situation in traffic, but a global. And here in this picture, the state of the whole system is represented by a ball, and the ball, of course, must overcome this mountain here, this energy barrier, and classically that is done by a kind of shaking the statistical system here. And but in the quantum world, we have a nice opportunity which is not possible in the classical world. Namely, we can push through the mountain here. And pushing through the mountain, that is the famous quantum tunneling. And that in the end is made possible by Heisenberg's principle. Because you remember, Heisenberg's principle, for example, said that in some cases it is possible with some probability that the particle is already behind the mountain. And that is used in order to realize here directly to the global minima. And you can imagine by this way, by this solution, we can avoid this detour on the mountains. And that means a lot of time which is not necessary, and energy. Here is a formulation of the Boltzmann machine in the quantum version. But now I want to highlight a last point. Namely, all that what I explained now is nowadays still simulated on a classical computer. Stimulated as a classical supercomputer here in the Leibniz Center 2. And that is the classical von Neumann architecture. And the classical von Neumann architecture means a strict separation between a memory and the processor. Since the Turing machine, that is the old architecture. And that means each bit must be stored here by the memory, and in the end, with increasing data stream and big data, all these data must be pressed through this architecture, and that needs a lot of time. It needs a lot of energy. So people are saying in the future, the near future, the largest part of energy will be used in digitalization. So digitalization is closely connected with our sustainability problems. It is closely connected with our energy problems, depending on this architecture. And that is sometimes called the von Neumann bottleneck. Like a ketchup bottle, the ketchup, these are the data which must be pressed through this bottleneck. And then on the other side, our brain. Unbelievable. 20 watts for all these crazy and amazing and impressing ideas and solutions of the human brain. And that is 20 watts, the energy of a lamp, a simple lamp. And how is that possible? One of the main reasons is the completely different architecture. No von Neumann architecture. The architecture I explained already, that is a network architecture. And in the network architecture, there is no separation of processor and memory. These two functions, memory and processing, is integrated in each synapse. A synapse can both. It can compute and it can process and it can store. And so the idea is, how can we realize this kind of architecture in hardware? Not only simulating like in machine learning. Nowadays the application of these networks is simulation on the von Neumann computer. How can we realize that? And the first idea was in the beginning of the 70s by Leon Schur. He is a US professor of electrical engineering from UC Berkeley. By the way, distinguished professor here at he's a former faculty of electrical engineering. And he suggested a so-called memristor, that means an integration of memory and storing and processor, and that was theoretically predicted by him, but later on realized in first steps. And we wrote a book which is here mentioned on the right on the mathematical theory of these so-called memoristic networks. So in the end, the idea is you get an electrotechnical model of the neurochemical working machinery of the biological brain. And now that is the reason that I'm now in the advisory board of a BMBF project at the RWTH Aachen concerning the so-called neuromorphic systems. That means models working such as in hardware, such as the human brain. But in that project, recently a new idea came up, and now I come slowly to the end of my talk, a new idea, namely not electronical realization of the model, but photonic realization. And that means that here you see a simplified neural network, and now the neurons are represented no longer by electrotechnical units, but by optoelectrical units here with photonic detectors and field effect transistors and things like that. I will not go in the details. And the interaction, the synapses, is here realized by photonic. That means light, that means laser light here, realized, for example, by the so-called Mach-Sender interferometer, which is roughly speaking a collection of mirrors reflecting the laser light. Now, in the end, we come to a neuromorphic system on a photonic basis, and now I come back to the quantum computer, because photons and photonic architecture can easily be combined with the quantum computing. And with all these advantages of quantum computing, quantum parallelism and tunneling and entanglement and whatsoever is possible. So neuromorphic computing and quantum computing, and that is the idea and the message here, reduce energy consumption for sustainable AI. That is in the end my message here. for today. The close connection of digitalization and AI nowadays, especially in the future, with our energy problem, and so the aim, energy consumption for sustainable AI. And with that, I will come to the end here, my last slide, with our flight with the owl of Minerva from philosophy to quantum computing and artificial intelligence and back. And in the center, I think the motivation should be sustainable and responsible AI. I thank you for your attention.